Good evening, welcome. So we're here to talk about continuous delivery pipelines, and I think that often when we talk about this idea, it's an idea that's become popular, and that's pleasant for me. I'm one of the people that well, I am the person that invented the term, but I think often they're kind of misunderstood. And certainly when I was thinking about what a deployment pipeline was about, it was about more than just some kind of build and test workflow. It's a bit more structured and a bit more organized than that. So I want to talk about that a little bit and explore that idea. I think that when we think about what it is that we're trying to do is, we're trying to optimize the development process in continuous delivery from idea to valuable software in the hands of our users. And because it's so hard to measure progress, we want to measure progress by finished changes, finished pieces of work in some way. And so the fundamental principle at the root of continuous delivery is the idea of working so that our software is always in a releasable state. And to do that, the deployment pipeline is a great organizing idea that allows us to facilitate that. So we're going to start off with some developers, and they're going to commit a change, and then we're going to carry out a series of evaluations to determine the releasability of that change. And I think that's the first thing that people commonly miss when talking about deployment pipelines. If you just go from the term continuous delivery, what most people assume that means is deploying into production all of the time. And certainly it enables that. It enables more frequent deployments into production more reliably. As the subtitle to 𝒍𝒊𝒌𝒆 and my book was repeatable, reliable releases of software into production through test and deployment automation. And certainly that's kind of what it's about. But I think more than that, it gives us this tool for really determining the releasability of our changes. So what we're trying to do is that we're trying to go from commit. We're going to generate a release candidate quickly, and then we're going to deploy that release candidate into an ever increasingly more difficult series of validations and run it and get it into production. And that's what we're optimizing for. And that's always what we're optimizing for, from commit to releasable outcome. That's really the game that we're trying to play here. And that kind of changes our focus somewhat on what that means. It means that we're trying to get the deployment pipeline as the only route into production, the definitive route into production, really. So all changes to production flow through the deployment pipeline, and that gives us control. Over the years, I've increasingly started to view this, and to some extent when we wrote the book, this was in the back of my mind, but I've increasingly started to view this as a genuine engineering discipline for software. What we are trying to do is that we are trying to optimize for fast, high quality feedback. And as a developer, the ideal situation to be in terms of being able to sustain high quality, efficient work, is to be able to get feedback multiple times per day that, yeah, your change is good, it's safe, it's good to go. And that's what we're trying to do. So we want to try and make sure that we get this great feedback clearly, efficiently, communicated to us. The next kind of step to start thinking about that then is that we kind of define, there are three different zones within the deployment pipeline that are of interest. There's the commit cycle, the acceptance cycle, and production. And I think that often people miss the value of this way of organizing things. When we structured the book, we had a chapter on each of these bits as well as lots of other things, and we were kind of defining these things. And I think that what most people took from the book was more kind of this idea of the deployment pipeline as kind of a build workflow or a test workflow. But certainly when I was writing the bits about this stuff, what I had in the back of my mind was explicitly these steps, these phases in the deployment pipeline. The commit cycle, first of all, is about evaluating changes that are going to support development. We want to give fast, high quality feedback efficiently to development teams to allow them to sustain a good pace of development of high quality changes. Then in the acceptance cycle, we want to evaluate our changes for releasability. And we want to do everything that it takes to get to a definitive statement on the releasability of our change. And finally, if all of that is done, we are free to go into production. What when you start kind of following this line of reasoning, it has some implications. It starts to say things about, the scope of a deployment pipeline. If we want our deployment pipeline to be definitive in terms of releasability, that means that we've got to do everything that's necessary to achieve that validation of releasability within the scope of the pipeline. So yeah, we've got to test it from the point of view of a development team, but we've also got to test it from the point of view of users. Does it fulfill user needs? And that's captured here in this picture in the acceptance test stage. Does it meet performance criteria? Is it secure? Is it, can the data migration work effectively? Is it resilient in the face of failures? Is it scalable? Is it compliant? If all of those things or any of those things are involved in determining the releasability of the change, we want to try and build those into the deployment pipeline. Ideally, as I said, we're looking to get feedback quickly and efficiently back to the team. So let's start looking at each of those bits in a bit more detail. The first stage of the pipeline is really the commit stage. And what we're looking for from the commit stage is really two things. We're looking for fast feedback that our change is good, and we're looking for a high level of confidence that if all of this testing works, everything else is going to be fine. And those are two kind of competing tensions in the needs of the commit stage. It's not good enough for it only to be fast. If it's fast, but it leaves us with low confidence, that's not good enough. And you're not going to gain that confidence if you haven't got fairly thorough testing. So you've got to have an awful lot of validation in there in order to be able to get the feedback efficiently enough for it to stay fast, to gain the kind of confidence that we're looking for. This starts to lead us in a certain direction of thinking of the kinds of stuff that we're interested in capturing or catching with the commit stage. Our objective is to fail fast. We'd like to be able to catch the most common kinds of mistakes as early in the process as we can. There's a slightly American phrase, which I confess I don't like very much, but it's shift left. We're trying to move all of the decision making as close to the developer as we can at this point. In general, I'm kind of jumping ahead of myself in terms of my presentation a little bit, but in general, what I recommend to my clients is that you aim for feedback from the commit stage in under 5 minutes. So in an ideal situation, we're looking to be able to build and test to the point that we've got a high level of confidence. I generally recommend about 80% level of confidence that if this change is good, everything else will be fine. And you do all of that in under 5 minutes. That starts to focus the mind a little bit about what that means in terms of what you can do. The good news is that some of the responsibility of the commit stage are eminently parallelizable. And so we can actually do a surprising amount of work if we put our minds to it in that kind of time. I was involved in a project where we built one of the world's highest performance financial exchanges at LMAX, and we put our entire enterprise system into one big repo. We built and tested everything together in the whole enterprise system in one repo, and our commit stage took 4 minutes to run something like about 35,000 tests against the system to give us that 80% confidence as a starting point. So that's starting to tell us some things about those tests. It's starting to tell us that they need to be efficient in some way. We can't afford those tests to be probably starting up a full version of the application at this point. We probably don't want those tests to be talking to a disk. Even a solid state disk is going to slow those down enough that it's going to start to compromise our ability to get through that much work. We probably don't want to be starting other processes or talking to a message queue or talking to a database or any of those things. And if your head has started to drift in the direction of unit testing and more specifically test-driven development, you're in sync with me. That's where my head goes when I start thinking of those kinds of things. So the easiest way to do this is with test-driven development. So because those tests are going to run in memory right next to the software that we're going to run, and actually within reasonable timeframes, within that 5-minute window, you can easily run hundreds of thousands of tests, even on a single machine, if they're written that way. And so that gives us this, a starting point of this fast feedback. That's not quite enough, though, and the reason why when Jez and I wrote our book, we didn't call this stage the unit test stage or the TDD stage or continuous integration, was that it needs just a little bit more than that, because we might need other kinds of validations to gain that level of confidence. So perhaps we want to validate that our coding standards are met, for example. So I quite like automating the coding standards, so that if I commit some code that doesn't meet the team's coding standards, it will be rejected on commit. Maybe there are some common kinds of failures that we see later on, failures that normally we only see at runtime. And so maybe I want to bring some kinds of tests just to kind of up the level of confidence. So we're permanently kind of playing this balancing game between getting the feedback from this stage as fast and efficient as we possibly can, and maintaining that high level of confidence that if all of these tests pass, everything else is going to be good. This starts to play the reason why we want this stage to be so fast is because this is kind of the amongst the most valuable real estate in our deployment pipeline. What we are trying to get here is we want developers to shift from making fewer, larger, more complex changes to making many smaller, simpler changes. That is very highly correlated with fewer defects and higher quality software. There's good data to back that up from the State of DevOps report and described in the Accelerate book. When organizations move more quickly, you actually up the rate of quality. That's counterintuitive, but it's true. So we'd like to start to think about encouraging development in these smaller steps. So what we'd like to do is that we'd like to be able to have developers commit a change, sit there, wait for the result from the commit stage so that they're ready to fix a problem if one occurs at this point. And if it doesn't, if everything's good, they're going to move on and start working on something new. If a problem does crop up at this point, then they're ready, they're on the case to react and fix the problem. This is kind of the initial version of this idea of maintaining our software in a releasable state. Our objective with the deployment pipeline is to use it as a falsification mechanism. However many tests we have, we can never prove that our software is good. But as soon as we have a single test failure, we know that our software isn't good enough, and therefore we can reject that to change. And that's the way that we want to try and use the pipeline and how we'd like to work. So as soon as there is a test failure, we're going to halt the pipeline at that point. That means that our software is not in a releasable state, and the whole priority now of the team is to get back to a stable position. What we're looking for is for whoever committed the change to be on the hook for fixing the change. It doesn't matter where the test failure occurs. If they committed the change, they are responsible for fixing the problem. So we'd like them to work in these small steps. And there's a few kind of rules of thumb that I like to apply to thinking about this at this stage. So generally, I advise teams to adopt a kind of 10-minute rule. So once you've identified a problem in the pipeline, wherever it might be, start a clock, and you've got 10 minutes to commit something. And either you're going to commit a fix for the problem that you've introduced, or you're going to revert the change that introduced the problem to get back to a stable, releasable state in the pipeline, and you can figure out the problem offline. And so there's a bunch of behaviors that a team adopts to start working and inhabiting this kind of territory. Test-driven development is one of the more significant improvements in software development that I've seen during the course of my career, in my opinion. And I think it's underused. And I just want to say a little sidebar on why I think that it's important. If you think about what quality is in code, I would argue that there are 5 things that kind of represent quality in code. There may be more than 5, but my bet is that you won't disagree with my 5. Whatever the nature of the code, whatever the technology, whatever the programming paradigm or the nature of the system, good code is modular, it's cohesive, it's loosely coupled or appropriately coupled. It implements abstraction or information hiding, and it implements separation of concerns. Each piece of the code is focused on achieving one outcome, one good one thing. So what does it take to put those properties into code? And I think in the absence of test-driven development, it's down to only the skill, commitment, or experience of an individual developer. It's down to whether they're good enough, whether they can be bothered enough, and whether they've seen how to solve these kinds of problems. Test-driven development is something very specific. It's different from unit testing. Nearly everybody that hasn't done it confuses it with unit testing. They're not the same thing. Unit testing is just testing small pieces of code, usually after you've written them. Test-driven development is very specifically driving the development process from writing tests. I like to describe it as red-green refactor. You're going to write a test and you're going to run it and you're going to see it fail. That's the red stage. Then you're going to do the minimum amount of work to get back to a stable passing state by writing simple code to get back to that stable state. That's the green stage. And then you're going to refactor the code and the test to make them beautiful, elegant, more general, better architected, better designed, while you're in a stable passing state. That's the refactor stage. So if you think about that, if you think about any developer working that way, they're going to write the test first before they start writing any code. And if you do that, you have to be a slightly unusual person to make your own life more difficult by trying to write tests for code that doesn't yet exist and making the code hard to test. So you're going to naturally try and write your test in a way that's going to make your own life easier by making the code more testable. You're gonna focus on that. And in essence, what this means is that at the point at which you are writing the test, your mind is focused on designing the code that you want to implement from the outside in as a consumer of that code. And that has a significant impact on the design of the code. The first thing that it does is it tends to make sure that the tests are slightly more decoupled from the code that you want to write, because you don't know yet what that code's going to look like. You haven't written it yet. And the next thing it does is it gives you feedback on the quality of your design. If your test is difficult to write, then it probably means your design is poor. And so you go back and you improve your design in order to make your test easier to write. But in the context of my 5 parameters for quality, what does this mean? Well, if you're going to start by writing the test first, you're going to inevitably create more testable code. So what are the properties of testable code? Well, testable code is modular, cohesive, loosely coupled or appropriately coupled, exhibits information hiding, and has a good separation of concerns. So test-driven development kind of acts as a talent amplifier for developers. It's not going to make crap developers great, but it will make bad developers better, and it will make great developers greater. However good you are, it will improve your code. I had the pleasure of working with a friend of mine who I consider to be one of the best programmers in the world. And I taught him to do test-driven development. And both he and I think that he's a better developer. He was always a good developer, always a great developer even. But both he and I now think he's a better developer as a result of applying this. So it's this fantastic tool that we can kind of drive progress forwards with. In implementing a commit stage, we've usually got these kinds of steps to undergo. If we've got a compiled language, we're going to compile something, in order to be able to test it. We're going to run the tests that we've created for that thing, well, for everything together to spot any problems. We're probably going to run some analysis tests to kind of static analysis of various kinds to give us feedback. Check style or find bugs in Java, lint style testing in other languages to give us fast but a different kind of feedback to the kind of feedback that we get from tests. And if all of that stuff passes, if all of that looks good, we're going to generate a deployable thing. We're going to generate a releasable unit of software. I call them release candidates. So we're going to generate a release candidate that from now on, that's what we're going to evaluate. The reason that we do that is that we're trying to be efficient. We're trying to maximize the efficiency of this process. So what we're trying to ensure, we've just done a bunch of work. We've just spent CPU cycles compiling this code and testing it. We don't want to burn more CPU cycles compiling it again. Plus, if we compiled it again, we might use a different version of the compiler, and we might introduce a defect that one of these tests might have found. And so that's error prone. So we've just spent time compiling it. If that's good enough and that's what we tested, that's what we're going to ultimately put into production if it gets that far. So we're going to build the deployable unit of software, whatever that may be, a jar file, a .NET assembly, a DLL, an executable, a tarball, or a Docker image, or a Kubernetes image, whatever it is that we deploy, that's the output of the commit stage. What the commit stage does is gives us feedback from the perspective of developers. It's kind of answering the question, does this do what we, the developers, think it was doing? That's good. That's really valuable feedback, technical feedback on the quality of our work, but it's not quite enough to know whether it does the right things from the point of view of an application. So now we want to evaluate that from the point of view of consumers of the system, users of the system. And so we're going to do acceptance testing. This isn't kind of manual sign-off style acceptance testing. This is automated acceptance testing. And our objective is to eliminate any need for manual regression testing by automating all of that stuff. My preferred way of organizing this is to create a domain-specific language that lets me captures the intent of our system from the perspective of a user of the system in this domain-specific language to express test cases quickly and efficiently. And then we're going to test those lifelike scenarios in a production-like test environment in the context of consumers of the system. To do that, we're going to need to deploy these release candidates, these bundled up deployable units of software, into this production-like test environment. So we need to automate the deployment. And since we're deploying the thing that we will deploy into production, we'd be foolish not to take the opportunity to use exactly the same mechanisms and as close as we can possibly get to the same configuration in our test environment as we will use in production. This way, we get to not only evaluate the behavior of the system, we get to test its configuration, check that it's deployable, that this change with these other changes are deployable, usable, and fulfill a user's need. So we can kind of implement that as part of the deployment, as part of the acceptance testing. We're going to run the acceptance tests, and we're going to capture the results of those, and we can tag the release candidate with the results of running those acceptance tests. Does the software do what the users want the software to do? And you can start seeing a pattern here. We've kind of now got these release candidates, and we've got an ever-growing level of confidence in the releasability of our system. Depending on what's involved in your system, what's in the acceptance testing or certainly in the acceptance test cycle can vary enormously. This pipeline on the screen is modeled after the LMAX pipeline where we built the exchange, and performance was critical. So we got 2 levels of performance testing. But we also did security testing within the acceptance test stage. We did scalability testing, resilience testing, and so on. As I said, we want to eliminate as far as possible any human regression testing. Human beings are too slow, too expensive, honestly, too low quality, not repeatable enough to do a good job of regression testing. We'd like to do way more regression testing than human beings, even an army of human beings are capable of. And so that's a job for machines. My favorite approach to doing this is that you drive the development from here. When you come up with a requirement in the form of a story centered around the desirable behavior of the system from the perspective of a user of the system, we capture a series of examples that represent acceptance criteria, how we would recognize that this value was delivered. And then for each acceptance criteria, we write one of these acceptance tests in the language of the problem domain. And then we do TDD, TDD, TDD underneath the acceptance testing until that acceptance criteria is met. And when all of the acceptance tests pass, we are done. And we kind of got an automated definition of done. The acceptance test stage tends to be implemented like this. We're going to configure the environment ready for use. We're going to deploy the release candidate into the environment. We want to start it up. We probably want to do a brief smoke test or a health check just to make sure it's ready for use. And then we'll run the acceptance tests. These first 3 steps, because we've got a release candidate and because we're going to deploy it the same every time, these are the same 3 steps that we're going to use from now on, whether we deploy into an acceptance test environment, a manual test environment, component test, or indeed production. And so we're rehearsing these all of the time, so we know that they work. I'm not going to talk any more about the detail of acceptance testing. I have a YouTube channel on which I publish videos once a week about software engineering, continuous delivery, and ideas like that. There's a whole section, there's a cluster of videos around behavior-driven development and behavior-driven approach to acceptance testing that go into the detail of this in a bit more detail. So if you're interested in any of that, tag along to my YouTube channel and take a look at those videos. As I say, there's a group of videos around those topics that you can kind of navigate to. I just said that, we're trying to optimize the feedback, and I said already that we're trying to determine the releasability of our change. We're going to try to optimize the commit stage to support development, so we're aiming for under 5 minutes. If we want to get to this releasable outcome, we've got to be talking about a deployable unit of software. If we need to test it at the end with anything else, then that's not really independently deployable, and that causes problems. So deployment pipelines start to give us some clues about ideas for dependency management. The most sensible scope of a deployment pipeline is an independently deployable unit of software, meaning that there's no more work to do at the conclusion of the deployment pipeline. So we put everything that constitutes releasability into the pipeline. If there's manual testing, component testing, performance testing, whatever it is, manual testing shouldn't be regression, it would be exploratory. So it's kind of slightly outside of the speed of the pipeline, but a useful adjunct sometimes to determine the quality from a human being's point of view. But what we're trying to do is that we're trying to get fast feedback all the way around. I generally recommend to my clients that you aim to get a definitive statement on releasability in under an hour. Why that? Why under an hour? Both of these numbers, both of these guidelines, these rules of thumb are kind of based on, I suppose, pop psychology. The 5-minute cycle is really talking about, how long as a developer are you willing to sit and wait for a result? We want the developers to wait for the result of the commit stage before they move on to something new, so that they are this is the most common place to catch an error, and so we want them to be ready to fix that error at that point. If you leave it 10 minutes, at 10 minutes as a developer, I'm starting to get a bit itchy. I'm starting to think, I want to be doing something else. I'm getting a bit bored watching this screen now, this build. And 5 minutes is too long, but 5 minutes is about the limit beyond which it starts to push on unwanted behaviors. If I am working the way that I described, red, green, refactor, commit, I'm doing that all the time, every day, I'm probably committing once every 10 or 15 minutes. If I have to then wait 10 minutes for a result, I'm not going to commit at that point, which means that the size of the changes that I'm committing are going to go up, and the level of risk that I'm committing something that's likely to destable things also goes up. So if we want to encourage people to do work in smaller steps, which we do because that's the higher quality outcome, then we want to remove the barriers to that. 5 minutes is about the limit of my patience. For 5 minutes, I will sit there, and after 3 minutes, I'm probably drumming my hands on the table or something. But I'm going to wait the 5 minutes. I'll be a good boy, do what I should, wait for the result, and then move on to something new. The hour is kind of similar but different. The hour is best characterized by a project that I worked on. So I worked on a project for a trading organization. We were building, mostly doing market making into exchanges all around the world. And the primary problem for that organization, we had a reasonably large development team looking after all sorts of different bits of software, but we had a very large C++ build. It took 9.5 hours to run the C++ build and run all of the tests. So what the organization did and had been doing for about 4 years when I joined them was that they would do the build overnight. So a developer would commit a change, they'd wait for the result of the change the next day. If an error occurred, the developer may commit a new change to fix that immediately. But that still means that the build is not going to be fixed until the following day, because it's going to do an overnight build. So the build is now going to be broken for half the time for each fix. A whole day in this case. What that means, the subjective, most of the stuff I talk about, I like to have data to back me up, and I don't have data to back this statement up. But subjectively, my impression is that if you work so that you are building something and doing an overnight build, first of all, on industry scale, that's pretty bloody good. But my observation is you're probably living with somewhere between maybe 5 to 10% of your tests always failing. A random 5 or 10% of your tests will always be failing. In the example that I gave in the trading company, people that had been there from the beginning said that in the 3 years that they'd been operating this process, there had only been 3 occasions ever when all of the tests passed. So what they did was each morning they'd look at the modules where tests had passed and allow those to be released into production, and they'd reject the modules where tests had failed. That's fine as long as the modules where tests passed didn't depend in some way upon the modules where tests failed, which sometimes they did. So they had instability in production as a result of this practice. Part of my job was to improve their software engineering practices in this organization. So I started working with the team that was responsible for their build and deployment systems, and we ended up coming up with kind of continuous delivery as a service for this organization. To cut a long story short, we did all sorts of investigations into how to speed this up. But to cut a long story short, we managed to bring this down to a commit stage that took 12 minutes, and everything else took 40 minutes. So the commit stage, the build and running a bunch of tests would work in 12 minutes. Everything else took 40 minutes from 9.5 hours. In the first 2 weeks that we made that change, we didn't change anything else in deployment approach, technology, nothing. All we did was sped up the feedback cycle. In the first 2 weeks, we had 3 builds where all of the tests were green, because we were giving the teams feedback quickly enough that they could stay on top of the problem. In the following 2 weeks and ever after until I left that company, every single day there was at least 1 release candidate where all of the tests had passed. So this feedback is absolutely crucial. The hour comes from the idea that, if the build took 2 hours and I'm a developer and I commit a change and I screw something up, I've now probably got, on average, maybe 1-2 more goes at committing something to fix the problem before the day's finished. If it takes an hour, then I've probably got 4 or 5 attempts at trying to fix the problem. And so I'm more likely to fix it. And it's that simple. By speeding up to this kind of rate, it almost completely changes the development team's relationship with their code and the stability of that code. So this is kind of important, being able to optimize for this high efficiency. As a side effect, I should point out, I mentioned earlier on when we were talking about the commit stage, we're looking for a high level of confidence. If you've automated all this stuff, it's really, really easy to measure that metric. You just measure how many commits, failed commit stages or past commit stages and then failed later on, and kind of correlate the two to give you the 80% number. So how do you start building one of these things? And in general, I'm going to describe this as though we're building a brand new deployment pipeline for a brand new software development, which is the easiest way of doing it. But actually, my advice for building a deployment pipeline is pretty similar, even if you're starting with a legacy system, a pre-existing system. You don't want to start by trying to, boil the ocean and fix everything. So we're going to break things down into smaller steps. And ideally what you're looking for is in essence, a deployment pipeline test case? Well, a test case for a deployment pipeline is a change of some kind. So we'd like a requirement, we'd like a simple requirement. Let's imagine that we've got a system something like this, or we're about to build a system something like this. We're going to try and identify a thin sliver of behavior from our system that's kind of representative of the architecture of the system without being comprehensive. It's just going to be a thin cut of the system that, forces us to think about all of the issues that are realistic in the context of the system, but are not so complex to be daunting or to get in the way of our ability to do this. And then we're going to develop that story, and alongside it, we're going to develop the deployment pipeline necessary to sustain it. So we're going to write some unit tests to sort of drive the development. And so we're going to implement a commit stage to give us fast feedback on those unit tests. And we're going to write some acceptance tests to evaluate from to deploy the software in some manner, so that we can evaluate it from the perspective of a consumer of this change. And it should be intentionally a really simple change, so that all of this stuff is really simple. And then we're going to deploy it into the acceptance test environment and run those tests. And then we're going to, at least notionally, deploy this into production. And the production might be fake. It probably will be at this point, because this is probably not a wholly usable system. But now what we've got is that we've kind of got a walking skeleton of the system, and we've kind of got a walking skeleton of our deployment pipeline. And this is the simplest that it's ever going to be. This means that it's easy for us to build our deployment pipeline in the context of something realistic, this story, but we're not kind of blinded by the complexity of the problem. This is kind of this is the simple system that we've ended up building and deploying, and now our deployment pipeline is just enough to sustain that and get a version of this evaluated into production. Now, from now on, we can start using this. We can start writing tests. It gives us a placeholder. We've made decisions about where we're going to put tests, so that developers can, they just need to follow some conventions, and their tests will be picked up and run, whether they're acceptance tests or unit tests or whatever else. We've got the mechanisms to start tracing things, and we can start elaborating on the deployment pipeline. We can start adding more and more behaviors that evaluate different aspects of the releasability of changes, while in parallel with us building on the system and adding more and more tests and more validations of the system as we work through. As I said, this is the best, easiest way to start with when you're starting with a blank sheet of paper. But I would advise you to approach this in the same way when you're doing this with pre-existing code. In that case, start primarily with a focus on acceptance tests rather than unit tests, but start doing unit tests for new work, and you can kind of drive out the commit stage with new work, and then you can start building on that. If you start following this pattern incrementally, very quickly, you'll get to surprisingly high levels of test coverage. Don't chase test coverage per se. Use the mechanism of evolving and growing your deployment pipeline to a releasable outcome to steer you in the direction of high levels of testability, rather than just chasing that as a goal in its own right. So we want to go from commit to releasable outcome, and we're going to optimize everything in our flow to sustain that. As you start buying into this idea, it starts leaking out. It starts touching on a whole variety of other things. We start thinking about how the requirements process works, and how that's best structured to fit in with our acceptance testing and the creation of this DSL. And that defines other aspects of the design of the system. All of this adds to our ability to create, maintain, and release measurably higher quality systems more efficiently using these sorts of techniques. So that's the end of my the presentation bit of this. If you want to follow more, if you want to follow up on any of the acceptance testing or some of the other stuff that I've talked about, there are lots of YouTube videos. I've got nearly 60 YouTube videos on my channel now covering different aspects, and there's a link here on the screen which you can follow. I'll stop sharing my screen at this point, and I'm more than happy to take any questions.
Thanks a lot for that. That was really good, really interesting. Just in terms of you know, when it comes to cloud development now, like, you know, and more, well, not just cloud, but more like infrastructure as code. You know, we focus on the software a lot now, like, you know, but obviously, you know, as we've got like machine images and we're using Docker, like, you know, and you know, we're actually you know, the actual infrastructure is actually code itself. Do you see, you know, what's your experience of seeing that being involved, like in terms of the level of testing of that type of code, you know, of that side of things compared to the actual software? Are you seeing, you know, historically I've not really seen it being, you know, tested like as much as really the software, but obviously if we're, you know, if it is code, we should be testing it to the same level of you know, or to the same level of scrutiny. You know, what's your take on that?
I think that you're right, that's kind of at the bleeding edge of what people are doing. It's not widespread. I've certainly done a fair bit of that and been doing that from fairly early on in my use of deployment pipelines. At the trading organization that I mentioned in my C++ example, I as part of introducing these ideas to that organization and getting stuff up and running, I worked very closely with the build and systems team that managed the build systems and test systems and all that kind of stuff. We ended up morphing into continuous delivery as a service team, which I think I said in passing. And you know, we've got a couple of thousand people using the tech to get stuff out into production, at which point this is a, you know, strategic resource for the organization. And so we, you know, we protected it. We got clustered systems for our deployment pipelines and full-on infrastructure as code for all of those things. We built a deployment pipeline for changes to our deployment pipeline. So it even had, you know, a mini kind of sequence of tests that it would run as a test of as changes to the deployment pipeline. Because if we made a mistake, we'd like to be able to recognize that mistake and step back to a more stable position. So we weren't going to destabilize people that relied on our services. So certainly that's where things have gone. That's where organizations have moved at the kind of leading edge of this kind of stuff. But I think I would agree with you that it's not kind of commonplace yet. I think it will be. I think, why wouldn't you do that? So one of the things that I said in the continuous delivery book, if you were foolish enough to let me loose in your organization, I could probably break your software faster by changing its configuration than I could by changing the code. But we tend not to test configuration changes. Why not? Why don't we? We should. So I think all changes should flow through the deployment pipeline, and that gives us an opportunity to test those changes. And then the deployment pipeline itself is kind of a dependency of the release candidate. You know, this release candidate was built with this version of the deployment pipeline. So if you kind of take it to its logical conclusion, you automate all of those sorts of things too.
Yeah, I think there's some people in the chat have said talked about a few tools, mentioned a few tools that we can use to do that, which is interesting. Certainly, it's like moved on a bit since I've probably looked at it in the last few years. Anyway,
so I can talk briefly about tools. I have to confess that I don't think tools are the real interesting bit.
No,
because you're not going to be able to buy any tools that are just going to make this happen. It's more all-encompassing than that. It's more about working practices and the way that you think about software development and the way that you approach it than it is about the tools. You can do it with simple tools. It doesn't take an awful lot of tooling to do that. What do you need? You need something that will run a build for you and report test results. You probably need a bit of scripting to join up, you know, who's likely culprits that broke things, and you probably want to automate the deployment and the configuration management. And you can do that kind of stuff with, you know, shell script or Ant if you want. You know, there are tools that are growing up around this, and some of them are moving in the direction of more sophistication. The early days, you got kind of Jenkins, Bamboo, those sorts of things, still useful, still reasonable tools of those kinds of first generation, probably second generation build management systems. TeamCity is my preferred one. It's a bit better in terms of the management of clusters of build systems and so on, although the UI sucks when you're trying to look at pipelines. These days, for more cloud-based stuff, for simpler stuff, you've got Circle CI, Semaphore, those sorts of places, GitHub Actions, those sorts of approaches for relatively simplistic pipelines. At the slightly more sophisticated end, you've got Spinnaker, Armory, Harness, who I should mention if I'm recommending them. I have a commercial relationship with because they sponsor my YouTube channel. But just for to be transparent about this, so, and I've never used them in a real project. I've only looked at them, so I can't recommend them other than say it looks like reasonable stuff from the outside. Yeah. Most of the cloud vendors have you know, AWS, Azure, Google, you know, they've got their own versions of CD, pipeline management things, and there's a bunch of stuffs around the edges as well. So things like deployment management and so on that are, I tend to think of some of those things as transitional tools, like the 𝒍𝒊𝒌𝒆 suite of tools, XL Deploy and those sorts of things. Good tools, but they're probably to help you get with, you know, for organizations with a legacy system to try and get you a leg up and move forwards. But actually what you need to do is relatively straightforward. I think it's as I said at the outset, it's not really solved by tools.
Just in terms of like an enterprise view on this, you know, so you know, we talk about pipelines, and to some extent there's a need for well, from an enterprise perspective, I think it probably helps if there's a consistent view, like, you know, on how you maybe you kind of manage pipelines across your enterprise. You know, I think probably it helps as having a starting point where you've got templates maybe which everyone can like adopt as a starting point, and then can evolve beyond that as they need to, from a, you know, to kind of like have like some sort of specialization for their builds. I mean, what's your view on that? You know, what's your view on having to like templates for pipelines from an enterprise perspective?
I think that there are two routes forwards, really, and let's start with the more conventional one first, which is what you're describing. I think you know there are kind of economies of scale, and you can take that surprisingly far. So, Google, for example, have 9.5 billion lines of code in version control, and they store nearly all of it in a single repo, and on every commit they evaluate the whole lot, logically at least. So that's quite an effective strategy, but you've got to invest massively in the engineering to be able to get feedback fast enough at that kind of scale. Google, you know, have kind of invested massively in things like distributed builds and cached builds to be able to sustain that kind of rate of feedback. But it works. It does. You can scale to those kinds of levels. I think from what I've seen, from, you know, as an outside observer, you can get feedback on any change in under 20 minutes from Google, I think, is what I read somewhere. if I remember correctly. They run millions of test cases every single day. It's just bizarre, the numbers. More prosaically, within an organization, so if you want to invest in that kind of level of feedback, if you're building bigger, more complicated systems, it probably makes sense to get some kinds of economies of scale and centralize the engineering effort so you can share it out. You don't really want every team doing their own thing in terms of deployment pipelines in that way, necessarily, let's say in a regulated environment, or if you've got complicated build problems where you can throw hardware at the problem and invest in it, in sort of building up these really high performance evaluation systems. So I think that kind of continuous delivery as a service is a good way to go for those sorts of organizations to some extent, and particularly if you're making the transition, if you're also at the same time, which most organizations that I deal with are, is you're trying to at the same time trying to achieve the cultural transformation and an engineering transformation to improve the quality of engineering alongside just the technicalities of building out the deployment pipeline. Having that centralized team, they can also be kind of evangelists to help spread the ideas a bit sometimes. I think that's a pattern that kind of works. There is an alternative strategy though, and we're all kind of somewhat familiar with it, and that's it's the more ultimately the more scalable one, and that is to decouple things entirely. So this is the Amazon route, where you essentially say that every team is independent and it's up to them. This is the genuine microservices route. It's one of the things that I think is misleading for many people about microservices, is that microservices are meant to be independently deployable, which means that you can evaluate them in a distinct deployment pipeline. But what most organizations that I see do that claim to be operating microservices, at the end of the deployment pipeline for the service, they then promote that to somewhere else and evaluate it again as some kind of integration test with other services. That's not microservices. That's a monolith. That's a different pattern. And if you treat it as a monolith, you have more options on how to optimize it than going the microservices route, because you can parallelize and do all the funky stuff that we've just been talking about. However, the genuine decoupling microservices route is the most scalable way that we know to scale organizations. Amazon are exceedingly unusual in that if Amazon doubles in size, it more than doubles in capacity, productivity, capacity to do work, and so on, because of these distributed teams. Essentially, from an information point of view, it's the difference between a distributed system and a monolithic system. You've got, the conventional build where you can, if you think about this in kind of computing terms for the technologists amongst us, the way that I tend to think about this is, the simplest system that I can build is single-threaded. But if I want to try and make it perform more, I'm going to do it multi-threaded. That's like having separate teams. And as soon as I've got multiple threads of operation, I've now got a coordination problem. How do I know that this version of change that this team's doing works with this other version of change that this other team is doing? And there's going to be a big cost to bringing those things together, in the same way that there's a big cost to bringing threads together in concurrent systems. The best way to parallelize problems is to genuinely parallelize them. So you distribute decision making, but for that's the most scalable approach, but that comes at the cost of losing control of consistency. So Amazon have traded off consistency for scale, and that works for them. But you can't have your cake and eat it. You can have both of those things, as far as I can see.
Thanks for that. Pete has asked the question, have you encountered any organizations that have elected to decouple microservices and then see teams that compete within the org?
Yes, I have come across some teams that do that kind of thing. And if you look at the way that the Amazon ecosystem works, that's exactly what they do. As I said, they've kind of traded off that sense of consistency. I saw a post from Sam Newman, one of my friends, sometime last year, and he reckoned that Amazon had made over 2,000 changes to AWS services during that year, last year. And that's an enormous rate of progress, in those services, new services that are being added all of the time to the AWS ecosystem. But if you look across those services, there's not lots of consistency. There's no coordination between the teams that are generating those services. So some of those services overlap in terms of function. Some of them, they have completely different styles in the way in which you administer them for, one service versus another. And that's because they are built on this distributed decision-making model. There's no coordination that brings the decision-making, centralization of decision-making.
But shouldn't the fact of like encapsulating logic and functionality in a microservice make it easier to have some sort of taxonomy around like what you're actually deploying, like delivering? I would have thought that's the case, but Pete's just sort of is agreeing with you in terms of like the number of AWS security services that they've got and choosing which one to use. But I would have thought like if you have gone down the microservices route, that it should expose like the amount of the duplicate services that you've got. If you're prepared to look at it and analyze it that way.
If you're prepared to look, and as soon as you start to look, and as soon as you start to make choices and constrain access, you're now slowing down those teams because there's more work. That's the point. So I'm not saying that either one is good and bad. It's kind of what do you want? Do you want more consistency or do you want more scalability? Because those are kind of the choices. I think that there's a limit to how far you can go in building complex systems that are coupled together. Think about it another way. So one of the ways in which I think about software engineering is fundamentally it's a discipline of two things. We should become experts at learning and discovery, and therefore apply ideas like science to being able to learn and discover and get feedback and experiment. And we should become masters of managing the complexity of the systems that we build, because complexity is the killer. So we need to compartmentalize systems in ways in which we can think about them in pieces. So there are various strategies to that. However we decide to go, we're going to, whichever route we go, whether we go to the fully distributed route or the independent route, at some point there's some level of coupling between these systems. If they're going to talk to each other at all, there's going to be some knowledge of what those other things do. So if we're going to manage complexity, we need to start thinking about, distrusting the boundaries of the systems that touch on other parts of the system, and treating those with a little bit more caution. One of the benefits of microservices, actually microservices says nothing about this. Microservices doesn't imply a particular technology choice. It's not REST or anything like that, but it's come to be sometimes, in some circles, it's sometimes seen as synonymous with that. But one of the keys to service-oriented thinking, I would argue, is that it makes a distinction between the boundary of the service, the point at which we interact with the service, and its implementation. We separate those things. And so that means that what we're aiming for in any system, whatever the approach, is that the protocols of information exchange between the services are more stable than the implementation of the services themselves. If we're sensible, that's one of the ways, one of the tools that we can use to manage the complexity of the systems that we create. And so microservices tend to do that, and they push it to the extreme. So if you genuinely follow the definitional terms of microservices and you treat them as independently deployable units, meaning you don't get to test them with other microservices, it means that you've got to treat the APIs to those services essentially as public APIs, because they are. You cannot force change on a consumer of the service as a result of you changing the service. So it gets you into the territory of hexagonal architectures and supporting multiple versions of interfaces on the services and all those kinds of things. So there's a cost to microservices to make them independently deployable, and more loosely coupled with respect to other services. And you want to try and engineer the protocols. So if you listen to the experts in microservices, people like Sam Newman, James Lewis, those sorts of people who were there at the birth of these ideas, what they say is that the way to do this is that first you design a more coupled system. You design your service-oriented system as a monolith, so that you can tease out what are good, stable protocols. Only at that point do you farm them off as microservices where they're more independent of one another. And that's the way that they say that you go. So then you come to the complexity. So the problem that Amazon, Netflix, those sort of the big web companies have is, if you look, if you haven't done this, I recommend that you go and Google microservice diagrams for Google or Netflix or something like that, and it almost looks like a star map. Any given organization of all of those services is ephemeral. It's because they're changing all of the time. Amazon are deploying new change into production once every 11.2 seconds. So every 11.2 seconds, the configuration of those services, the version management between them, is changing. So it's a dynamic picture. So you don't have that stability in the same way in those sorts of systems. So even answering your question, is this service better than that service, is really hard, because they're moving all of the time.
True. Any other questions for Dave?
Yeah, I have one question. Hi, this is Anish here. I'm joining from Bangalore. I thank you first, today for the great session. I think it's exceptional. Thank you.
Thank you.
My question is related to requirements granularity. I mean, in the context of continuous delivery, when we are, focusing on continuous integration and delivery, I mean, it's important that requirements should be granular, so that a developer can check in every day and get some feedback and things like that. But it's not much talked about. I just want to take Dave's opinion on that. What's your experience on that?
Yeah, so I think you're right. I think that this desire for working in small steps is kind of contagious. So it's and that draws you in the direction of wanting smaller and smaller requirements to work on. The ideal kind of story size for me is something that I can complete in a couple of days, maximum. That doesn't, though, determine my commit frequency. So when I'm talking about committing every 10 or 15 minutes into my deployment pipeline, to master, to trunk, to origin master, whatever you want, your main line to production, I'm not saying that I'm finishing whole features in that time. What I'm saying is that I have bought into continuous integration. So continuous integration, when it was originally kind of identified and described in the late 90s by Kent Beck and his team, was described as, imagine working as part of a team, and I make a change and you get to instantly see my changes and all of your teammates' changes and see the impact on your work. That would be a much nicer position to be in terms of working to move forwards. So the idea of continuous integration is to get to as close to that ideal as we can. The problem with branching is that branching is designed to isolate change, and so is kind of at the opposite end of a spectrum in some ways from continuous integration. When you start thinking about continuous integration in the context of continuous delivery, that starts to challenge us, because now if I'm committing these small changes multiple times a day, what that means is that that change should be releasable into production. If we kind of, I tend to follow kind of definitional terms on these things because I think it helps, and that's part of the definition of a deployment pipeline. We get to a releasable outcome, so every commit should be releasable, is what we're trying to get to. If that's true, that means I've got to become comfortable with the idea of committing a change that doesn't yet add up to a whole feature, but will be deployed into production and is still safe and tested and is not going to harm anybody else or anything else. And so that brings us into the strategies that are kind of starting to become a little bit more well-known. Things like dark launching, where we release a change but we don't actually connect it up to anything that anybody's using yet, or at least not to the the user interface. Or branch by abstraction, where we're able to kind of plug different behaviors in, old versions and new versions. And the best known one of all, feature flags, where we can kind of selectively switch on and off different parts of the behavior of the system. And that's the compromise of continuous integration. That's the cost of continuous integration, being willing to work and maintain our software in a releasable state. That kind of frees you now. So now, even if my requirement did take me 2 weeks or a month or whatever it was, it wouldn't compromise our ability to sustain continuous integration and continuous delivery, but it will change the way in which I approach my work.
So I have just one more thought, which I just want to share with you, Dave.
Sure.
See, this is one perspective, right? There's another perspective also, that the way traditionally you have been writing your requirements, right? It was not vertically sliced. I mean, you are just taking a big feature, you're writing it in such a way that you typically take 2 weeks for a feature to be delivered. But there's another way as well, where you really have some kind of a prototype done, some architecture spikes done, and ensure that you write your story in such a way that it can be typically, developed faster. And then incrementally, when you develop, you're developing the bigger feature as a whole together. So, I mean, I'm saying, as you said in the talk, shift left. I mean, look from a requirement perspective, look into better techniques in which you write, right? That's what I meant.
Absolutely, 100% agree with what you say. And I think that one of the, I've said a few times, I think that continuous delivery is an engineering approach to software development. And what I mean by that is that, like other fields of engineering, I don't mean this in the kind of lightweight sense of, just applying engineering name to what software development is. I mean it in the specific sense that if you follow this practice, you improve your chances of success. And part of the reasons for that is because if you really strictly start to buy into some of these disciplines, it forces better outcomes. So one of the outcomes that you're talking about is exactly that. So if I want to be able to write effective acceptance tests that evaluate the behavior of my system from a perspective of a user, then what I'm interested in is capturing the requirements as only those that are visible from the perspective of a user. So first, I'm going to stop doing horribly, horizontally layered requirements. I'm going to do these thin vertical slices that are observable by a user of the system. And as you start getting into that, you want to encourage small, fast changes, small, clear feedback, all of those sorts of things. And so you're going to tend to prefer shorter, faster stories, requirements to implement. And so there tends to be a positive pressure in that direction implied by the working approach. As an aside, there's so I see people struggle with this all of the time, because what people are thinking about when they think about user stories are, a more traditional, complete, holistic picture of everything that the user wants. That's not it. The idea of a user story is what you said. You just want this real thin sliver of observable behavior from a user's point of view. And it might be artificial that this is an increment in behavior, but you can use that as a powerful step forward. There's a fantastic book from one of my friends, 𝒍𝒊𝒌𝒆, called 50 Quick Ideas to Improve Your User Stories. And I have that on my iPad, so that when I get stuck, I can look up suggestions in there, because what he's done is him and David Evans, who wrote it with him, they've broken down a series of different strategies for decomposing bigger stories into smaller slivers. And there's a whole variety of different techniques that you can use to achieve that outcome. I've done that in some really unusual circumstances, and it's real powerful stuff, but incredibly valuable to drive the flow of change much more effectively.
I think it's a very, very good tips on that side. 50 tips for, can you say that name again?
50 quick ideas for user stories by 𝒍𝒊𝒌𝒆. I will try and put it in the chat.
Sure, that would be great. Yeah. Sure. Can I ask one more question?
Yeah.
Another question is, I work on basically my major part in embedded automotive domain. And one of the other things which I also observe is that the way our architect, one part which you covered widely is on the microservices part and things like that. But there are also systems which are embedded in nature, where architectures are not designed fundamentally for continuous delivery. I'm saying you are not designing your system that tomorrow this has to run into a system or in a build pipeline. So there should be a thought coming in, maybe as a architecture or architects also, that, hey, when the system is also designed, you're talking about continuous delivery also as a perspective, and the architecture is designed also. So that thought, it's not a post, you have delivered, you are now started coding. Now here you think about, okay, now I have to focus on, integrating this and so on. So that thought process should be also built in at the beginning, that how to talk about deployment as a whole and how to talk about that. So that is something which is, I just want to know, not only from microservices perspective, your thoughts on that side as well. I mean, I heard Len Bass talking about in his book on DevOps and architect perspective, but maybe more examples and things like that would really help. Yeah.
Yeah, and first thing is, again, I agree with you. I think that's absolutely right. Is that the value of this way of working is so high that we should be willing to pull any of the levers that are necessary to achieve it. In my view, there's there's a measurable economic impact to working this way. Organization, the data from the State of DevOps report says that organizations that work this way make more money than organizations that don't. And there's lots of other knock-on benefits. It creates higher quality. The way that I put it in kind of soundbite terms is, it helps you to create better software faster, and it genuinely does that. But to get to maximize those benefits, you have to kind of buy in, and you engineer your systems to sustain continuous delivery. It changes the way that you architect them for the better. So Barry kindly plugged my book at the start. I've just submitted a book that will be published later in the year to my publishers, which is on the topic of modern software engineering and how to do some of this stuff. And one of my arguments is that you can use ideas like testability and deployability to drive software architecture. You use those to help you to define the software architecture. And when you do, you get higher quality systems. The best system that I've ever worked on is the one that I alluded to, the exchange that we built. It was one of the highest performance, it is still one of the highest performance financial exchanges in the world. We built it, we started building it in 2007. And it's the best system, it's the best tested system that I've ever seen. It's the nicest system to work on that I've ever seen. And I got some feedback from somebody that still works there now, who says it's still the nicest software that he's ever seen. And that was largely, I believe, as a side effect of the way in which we applied these ideas. We were fortunate in that we started work on this project while I was in the middle of writing the continuous delivery book, and I was head of software development. So I was able to kind of, brainwash my colleagues to start applying these ideas from scratch from day one. And that's the nicest way to be able to make this change. It's much more difficult to to retrofit this to pre-existing systems for the kind of reasons that you're saying, because I kind of like Michael Feather's definition of legacy systems, which is systems without tests. So these systems weren't designed to be testable. They weren't designed to be deployed in the kinds of timescales that we're talking about. My system was, and so it was testable in minutes for a big, complicated, real-world system. With ridiculous performance characteristics. We did performance testing, whole system performance testing, all of those things in under an hour. So I agree with you that the logical conclusion of this is architecture 2 is a tool that you can use to make it easier or more difficult. And more than that, working in a continuous delivery way, as treating it as an engineering process, a discipline that you stick to, tends to force you in the direction of creating systems that are higher quality as a side effect because of these sorts of reasons that we're talking about, I believe.
Okay, Dave. Your latest book is released, Modern Software Engineering. Yeah,
I expect it to be published probably in September or October. It's just gone off to the publishers in the first draft, so there's a little bit of time yet.
But there's a link at the top of the chat to Dave's book that's recently been released, which is basically a lot of what we've been talking about today. It's quite interesting because we use the word like choice quite a few times in the last few questions, and that's a nice segue into the next webinar. But before I do that, I'd just like to say thanks a lot to Dave and everyone who came along today. I think that was really interesting. And we're going to have a video up on our YouTube channel as well. And obviously Dave's put a post up or did a link to his own YouTube channel, which we'll send out after this as well. In terms of the next webinar, which will be in May around, I think it's almost the same time here, same date. We're going to have a guy called Ben Ford, who used to be a Royal Marine Commando, and he talks about the OODA loop, and how he's done some work on that and how he's used that to help in his work with leaders and managers of large enterprises make better decisions and adapt much more faster to the changing environments which we now find ourselves in. So yeah, I'll send out a link to that in the next few days, and I hope that you'll come along to that. But yeah, it's quite interesting that we spoke about choices in the Q&A quite a lot, and obviously so choices around architecture, and pipelines, and that is all helps us to become a lot more adaptive if you make the right ones, that is. So anyway, thanks a lot everyone, thanks a lot Dave again, and really appreciate that, and enjoy the rest of the week, and look out for the next webinar.
Thanks Barry.
Thank you.
Thank you everyone.